says, for the voltaic cell pictured below, write the highest cell potential possible for each of the oxidation and reduction half reactions. Add up the half reactions to cancel the electrons and get the overall reaction. The direction of the electrons is correct, which means in the actual problem, you'll see the electrons are going just like we've drawn them in previous problems. The oxidation half reaction will be in the left beaker. And the reduction half reaction will be in the right beaker. That doesn't have to be like that, but for simplicity's sake, that's how we will do it. I will also point out that in previous voltaic cells, we've had platinum as an inert electrode here. We had iron in the last one. Now we've got carbon solid, which will be graphite. And graphite is another inert electrode. Just like platinum. Good. Just like platinum. So if you look on the standard reduction potential table, you will not find any reactions that involve carbon. Carbon is inert. It does not react. Now this problem, so we can look here to see what is oxidized. It is a general rule of thumb that metals are oxidized and generally metal ions are reduced. Doesn't always have to be that way, but that is generally how it is. We've got one metal here. And if we do the process of elimination that I talked about last time, if you start at the very bottom of our standard reduction potential table with the most negative reduction, and think about that oxidations will be flipped and therefore be the most positive at the bottom. As soon as we see magnesium at minus 2.37, well, flip this reaction, that will be plus 2.37 volts. That's going to be our oxidation. Oh, and I've written it as it was going to be on the sheet, but it needs to be magnesium solid goes to magnesium 2 plus 2 electrons. E is the electrostatic potential, but E is for the oxidation, the voltage of the oxidation, or the cell potential of the oxidation, is 2.37 volts. For the reduction, zoom in on what we've got in our solution. Take a look at our, may have zoomed in too far there. There we go. So we have Fe3 plus, Fe2 plus, lead 2 plus, and hydrogen ion, and chloride ion. And what we're going to do is we're going to start at the top this time because we're looking for a reduction half reaction. And we're going to keep going until we find something we have. We do have nitrates, but they're only in the salt bridge, so that won't count for us. And we get to, excuse me, Fe3 plus. One of my favorite reduction half reactions. We have Fe3 plus. That will be the most positive thing that we can do. Excuse me. So we'll write that out now. And our reduction half reaction potential, 0.77 volts. And checking in with the question what we've been asked. So write the highest cell potential possible for each of the oxidation reduction half reactions. Check. Add up the half reactions to cancel the electrons and get the overall reaction. Let's do that next. Jump in anytime if you have questions. So adding up the half reactions. Here's where things get interesting if they weren't already. I have 1 electron in my reduction half reaction. I have 2 electrons, in my oxidation. Electrons must exactly cancel. So that means that I have to multiply this reaction, this reduction reaction, half reaction, times 2. And what's different about cell potentials is you do multiply everything times 2 here, but you do not multiply the potential. And I went over in the lecture outline a little bit about why that is, but the first thing we have to know is it's not like delta H or delta S or delta G. When you double things, you have to double the delta H value, say. So do not double this cell potential. But then if I have 2 times my electrons, that means my electrons will cancel out. And I have my overall reaction will be magnesium solid plus 2 iron 3 ions. Goes to magnesium ion plus 2 iron 2 ion. And I straight add my oxidation and reduction half reaction potentials, and I get a nice voltage here. So it's going to be 2.37 plus 0.77. I get 3.14 volts. Let me zoom out a little bit. We can check in with our problem statement. Might have to zoom out a little more. For our problem statement, it says, okay, now we've added up the half reactions and get the overall reaction. Yeah, actually, that's the only last bit of question there. So now I will ask, does anybody have any questions about this process? Since we're done.